Swayam Prabha. Digital India. Educated India.
Okay, well, let me start by wishing you all a very good morning. Well, you see, the lectures are going to be on introductory quantum chemistry, roughly at the third year BSc and first year MSc level. And this, of course, is my address and affiliation there on the screen. Well, before I start my lectures, I would like to acknowledge a few people. This is my own department at the Indian Institute of Science, Bangalore, one of the oldest departments of chemistry in the country. And of course, I mean, I am here because of Professor Mangalasundar. I actually should have given these lectures in Bangalore, but I mean, it's better to come here, I thought. So, Mangalasundar, then of course NPTEL, and then as I proceed, you will see that I have taken material from Tintin Comics, YouTube, this website, and several other websites. I mean, I have, as far as possible, I have tried to acknowledge them. If any acknowledgement is missing, it may be pointed out to me, and I shall try to put in the references. So, the first 3 or 4 lectures will be very, very introductory. It will hardly use any mathematics, but it will give you an idea of why quantum mechanics is strange and at the same time absolutely beautiful. So, that is the aim of the first 3-4 lectures. In fact, when a student, particularly a student of chemistry, encounters quantum mechanics, it is a rather frightening thing. Students are not too happy with it, and many times teachers also are not too happy with it. And so, it is supposed to be a very frightening thing, something like the next picture that you are going to see. This is essentially because you see, one looks at the mathematics, one does not try to understand the physics, the physical situation. But if you try to understand the physical situation and then understand the mathematics, things become much better. In fact, it is a very beautiful subject, quite nice and beautiful, one of the most beautiful subjects ever developed by human beings. In fact, I would say that it is much more beautiful than the next picture that you are going to see. Of course, I mean, you may say that is my personal opinion. It in fact is my personal opinion. So, here is an outline of what I am going to describe in the first few lectures. I shall start with this question, wave or particle. I am sure you would have heard about this microscopic things like the electron or the proton or the neutron. Any of these things have a dual nature. They have a particle nature as well as a wave nature. So, I shall try to illustrate that. I shall try to make the ideas clear by describing what are referred to as two slit experiments. Okay. And then I shall talk a little bit, I mean, we will discuss uncertainty principle in more detail later, but I shall talk a little bit about the uncertainty principle and then go to what are known as standing waves, okay, what are known as standing waves. Then talk about stationary states, atomic orbitals, and ask this very interesting question, do we understand quantum mechanics? Right. I am sure you would be surprised by this kind of question at this point. Then I shall talk about an approach which is not usually used by chemists. It is known as the path integral approach. In fact, again, in my opinion, it is one of the most beautiful things and we discuss its connection with the random walk. So, this is an outline of the first 3 or maybe 4 lectures. So, what about 2 slit experiments? Well, to do a 2 slit experiment, well, you see, what we will do is we will imagine that the 2 slit experiment is done. First, we will imagine that it is done with the particles. Okay, and I am sure all of you will agree that bullets are particles. We have absolutely no doubt that bullets are particles. So, I shall imagine, of course, this is a hypothetical experiment. Nobody who is in the right sense will ever do this experiment, and without doing the experiment, you know exactly what is going to happen. Okay, then so we will imagine that this is first done with particles, and then we will think of what happens if the same experiment is done with waves. Okay, there of course, I mean you have to do the experiment to get the results, and then finally we will ask what will happen if you do this experiment with electrons or other microscopic things, and the answers are very interesting. So, let us imagine that we are going to do this experiment with particles, in fact bullets. If you want to do a 2 slit experiment with bullets, then obviously you have to have a source of particles, which in this case of course would be a gun. So, imagine that you have a person who is having a gun, and there are 2 slits. Here are the 2 slits, and this person who is guiding the gun, he is going to shoot out bullets. Just to make things interesting, you can imagine that he is drunk. So, he is going to shoot out bullets in random directions, and you have these 2 slits. So, what is going to happen is that only some of the bullets will be passing through the 2 slits, and whenever a bullet passes through a slit, what is going to happen? It is going to be incident upon this wall here, which I am going to refer to as the backstop. And whenever a bullet hits the backstop, it is going to leave a mark on this backstop. And as I said, this is an imaginary experiment, or a thought experiment rather to say. And so therefore, because it is a thought experiment, I can imagine that he is given maybe 100,000 bullets, he shoots out all of them, maybe 5,000 of them will pass through these 2 slits and will be hitting the backstop. And so, after he has done this, what will I do? As a scientist, I will go and look at the marks that have been made by the bullets at the backstop, and plot a graph. I mean, that is what scientists would normally do, and plot a graph which shows how these marks are distributed on the backstop, and I shall refer to this as an intensity distribution for the bullets. Okay. So, if you did that, what would be the result? Okay, there he is shooting out the bullets, and in fact, this figure is taken from that particular website. So, here is a schematic arrangement of the results that you will obtain. There are these 2 slits, and I am going to imagine that only this slit, that is slit number 1, is kept open, while the other slit is kept closed. And so, what is going to happen is that any bullet that reaches the backstop would have passed through slit number 1, and most of them, what is going to happen is that they will arrive somewhere in this location, somewhere in the vicinity of that point. But it is also possible that a bullet might hit an edge at this location and be deflected, and perhaps once in a while a bullet may arrive at that location also because of deflections. So, as you plot the intensity, what are you going to get? You will get a curve which has a maximum like the one that is shown in the figure, and as you go away from the maximum, the intensity will decrease, and I am going to refer to this intensity distribution as I1. Why the subscript 1? Because I am keeping only slit number 1 open. So, suppose instead of doing this, I had kept only slit number 2 open, what would be the result? This curve shown with the red color would be the result, and I have called it I2. Okay. Now, suppose you do an experiment where both the slits are kept open, then what is the result? I mean, you do not have to actually do this experiment to say what the result will be. At any point bullets will be arriving. They might have passed through slit number 1 or they might have passed through slit number 2. If they pass through slit number 1, the intensity distribution is I1, while if they pass through slit number 2, intensity distribution is I2. So, I12, right, the intensity distribution in the case where both the slits are open, I will denote it by the symbol I12, and if I wanted to calculate it, what should I do? I will have to take the sum of I1 and I2. So, I12 obviously will be the sum of I1 and I2, and that is simple and straightforward. And not only that, you see the bullets have another very interesting characteristic. You see, I will always be getting one bullet or 2 bullets or 3 bullets, 4 bullets and so on. I do not ever get fraction, right, I do not get fraction. So, see the bullets have something which may be referred to as lumpiness, right. If I am doing an experiment, I would have 100 bullets or the next possible number of bullets is only 102, I do not have 101.5, okay. I would have 100 bullets and 101, then 102, 103 and so on. So, bullets have what I may refer to as lumpiness, that is a characteristic of particles. Okay. Now, suppose I did the same kind of experiment with waves. This experiment one can actually perform. How to perform it? You can imagine that you have a large trough of water here, and I will have something that is vibrating, right, something that goes up and down on the surface of water, maybe a pencil or something I attach to an electromechanical device. The device causes the pencil to vibrate, and as it vibrates it will penetrate, I mean it cuts the surface of water. So, that is my source of waves, and then here I will have a wall which will cut the surface of water, or a board or something which will cut the surface of water, and on that I am going to have 2 slits, so that the waves that I have produced there can pass through these 2 slits and be detected on the other side. So, that is the experimental arrangement that you have to imagine. And what is the result? Well, if you schematically represent it, you say you have the 2 slits 1 and 2. If I kept only slit number 1 open, what is going to happen? You will get an intensity distribution which may be represented by this green curve called by the name I1, and if you kept only slit number 2 open, what do you get? You will get this curve, red one, denoted by the symbol I2, and the question is what will happen if you keep both the slits open. In the case of bullets, it was clear that you can get I12 as the sum of I1 and I2, and is that what you are going to get? Well, this is not the result if you are going to do the experiment with waves. The result that you get is not this. You cannot get I12 by adding up I1 with I2, and the actual intensity distribution that you get has a series of maxima and minima. In fact, there are points, for example, a point here or a point there where the intensity is extremely low, close to 0, but there are also points here or there perhaps where the intensity is somewhat large. So, you get a series of maxima and minima, and I am sure you know the reason for this. This is essentially because waves exhibit the phenomenon of interference. Okay, waves exhibit the phenomenon of interference, and that is the reason why this happens. I shall explain this in a little bit more detail. So, it is obvious that if I wanted I12, I cannot get it by adding up I1 with I2, and the question is how will I get I12? If I wanted to calculate I12, what is the thing that I should do? Well, let us imagine that I have only one slit open, and in such a situation what is the result? Well, I have kept only one slit open and you can see that the waves are coming out, through this slit and they are spreading. And suppose I am sitting here and trying to look at the waves, then I will find that there is some intensity for those waves at that point, and if I wanted to calculate the intensity, I mean I am not going to go into the details of wave physics, but if I wanted to calculate the intensity roughly, you can say, well, the intensity is actually dependent upon the displacement of the water surface at that point. But displacement, as you know, can be in the upward or in the downward direction. So, what would you expect? You would expect that the intensity has to be dependent upon square of the, it has to depend upon the square of the displacement of the water surface at that point. As I said, I am not going to giving you all the details, but roughly speaking, it has to be proportional to the it has to depend upon the displacement square. It has to be a quadratic involving displacement. So, therefore, you see, if I have only slit number 1 open, what should I do? At any particular point, maybe a point here, what I will have to do is I will have to look at the displacement and I will have to think of calculating the intensity using the square of something that is quadratic in the displacement. And that displacement, I am going to denote a displacement. Naturally, you would expect that it should be called a d if I am going to give a notation, but just for the sake of convenience, I am going to call it psi, because essentially eventually psi is going to come into our discussions. So, therefore, what will happen is that I will say, okay, I1, why should I put the subscript I1? Because only slit number 1 is open, and if I wanted to calculate the value of I1, what should I do? I will have to find the displacement at any particular point and take its square, calculate its square essentially, do something with psi square essentially, I shall get the intensity. As I said, this is not the complete description, but this is enough for our purpose. Suppose instead of keeping only slit number 1 open, suppose you had kept slit number 2 open. What would be the result? Well, all that will happen is that at any particular point there will be a displacement caused by the waves which have passed through this slit, and that displacement I am going to call it psi 2, and naturally the intensity I2 will be dependent upon psi 2 square. Okay. And now suppose I keep both the slits open, right? What is going to happen? Well, if you kept both the slits open, this is how the displacement would be. If you plotted the displacement as a function of position, this is how it is going to be. You can see that, say for example, somewhere here there is hardly any displacement, while somewhere there you will see that there is large displacement, right. Why is it so? The answer is actually extremely simple. I have kept both the slits open, the waves can pass through both the slits, and at any point what is happening is that there are waves which have passed through slit number 1 and arriving there. There are also waves which have passed through slit number 2 and arriving there, and the net displacement at this location will be due to these two waves, and the displacement due to the first one is psi 1, displacement due to the second one, let us say it is psi 2, then what will be the total displacement? Total displacement has to be the sum of these two. So, therefore, we have this equation which says that psi 1 2 must be the sum of psi 1 and psi 2, and what can happen is that you see psi 1 and psi 2 may both be in the positive direction, in which case you will have a large displacement, while it may happen that psi 1 and psi 2 may be having opposite signs, in which case they will cancel each other and you will have very small displacement. So, that is the reason why you find that you see in these regions there are, in this region or in that region there is hardly any displacement, while in this region there is a fairly large displacement, and therefore what will happen if you look at the intensity as you know is going to be calculated as, or it will depend upon the square of psi. So, naturally if psi has a small value, intensity also would have a small value, and that explains how you get this particular interference pattern that we saw earlier. So, this is the pattern that you will get. Now, suppose you did exactly the same experiment with electrons. So, how will you do the experiment? You will imagine that you have an electron gun. So, the electron gun is going to shoot to give you electrons. What you will have to do is, I am not going to go into the details of the experiment, but you will have to select electrons, all of which have the same energy, and pass them through an arrangement of 2 slits, and you will have to detect where they are arriving on a screen. Right. These things can be done these days, there is no problem with that. The only thing is that you see you cannot do it in this room, because this room has air. If I produce an electron, the electron will not go anywhere, it will collide with the molecules and will go off somewhere. So, you have to do this experiment in ultra high vacuum. And not only that, these days you see we have detectors which are extremely sensitive, they can detect even the arrival of a single electron. Okay. So, such an experiment was in fact done. I will give you the details of the experiment in a few minutes. So, what you do is you say that okay, this is my source of electrons, these are the 2 slits, and this is the screen on which I detect the arrival of electrons. If I kept only slit number 1 open, I will get this intensity distribution which I shall refer to as I1. Well, if I kept only slit number 2 open, you will get I2. And in fact, as I told you, it is possible to detect the arrival of electrons one by one if you want. You can actually see where they are arriving, as you will see in a video which I am going to show you, and you find that electrons actually arrive in lumps. You do not get half an electron, you get 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on. So, therefore, in that sense electrons actually resemble bullets, and bullets are particles, right. So, they seem to be similar to bullets, and therefore, if I use that and ask the question, what will be I12? I12 is the intensity distribution in the case where I keep both the slits open. What would be the expression for I12, and what would be the answer? Obviously, it has to be the sum of I1 and I2, it has to be. So, the expectation is that I12 must be the sum of I1 and I2, but if you actually do the experiment, you do not get the result to be this sum, but what you get is actually an interference pattern. So, even though electrons are like bullets in that they arrive in lumps, the intensity distribution that you experimentally find is not characteristic of particles, but it is characteristic of waves which exhibit interference phenomenon. Okay. So, in this case I1 plus I2 is not equal to I12, but suppose I wanted to calculate I12, what should I do? Well, it means that you see, just like we thought of the wave function, so to say, the wave function in the case of water waves, what was it? It was actually the displacement of the water surface. Just like that, you have to imagine there is something that is associated with the electron, which we will refer to as the wave function and call by the symbol or denote by the symbol psi. What is the use of it? Well, the use is that if from it we can calculate the intensity, okay. Number of electrons arriving at a particular location, I can calculate from this psi, and it so happens that in the case of electrons, all that you need is you take the wave function the psi and take its square, you will get something that is proportional to the intensity. Okay. So, that is something that we will have to assume. In fact, instead of saying that it is proportional, I have just said that it is equal to, but strictly speaking it is proportional. Okay. So, I12 is the intensity of electrons arriving at different locations on my, when I say intensity of electrons, it essentially means number of electrons arriving per unit area. So, I12 we can calculate from a knowledge of the wave function, and it will be, well, strictly, as I said, strictly speaking, there will be a proportionality constant also, but for the sake of simplifying the notation I have omitted that. So, I12 is actually equal to psi12 square. But if you wanted to calculate psi12, what will you do? Just as in the previous case, what you will have to do is you will have to say that psi12 has to have two contributions, one coming from things that have passed through slit number 1 and the other coming from things or waves which have passed through slit number 2, and therefore, psi12 must be the sum of psi1 and psi2. So, what is psi1? We will say that it is contribution to the wave function of the electron from the waves which have passed through slit number 1, and psi2 again similar thing, contribution from the waves which have passed through slit number 2, and these two contributions I have to add together. I am going to get the total wave function, and once I get the total wave function, what should I do? I should take its magnitude and square it. I am going to get the intensity. Okay. This is the address where you should have a look at, and the experiment that was carried out by these people is the one that is shown in this picture. They have a source of electrons which produce mono energetic electrons, that means electrons all of the same energy, and they had a very thin wire. Okay, here is the wire, it is only 1/1000th of a millimeter thick, and the electrons from this source can pass through the left side of the wire or through the right side of the wire. So, essentially this is our slit, and they are incident upon a detector. This detector is actually capable of detecting the arrival of a single electron. This was essentially developed by the Hitachi company, and so the experiment was carried out in the Hitachi company in Japan. So, what I am going to show you is a video taken from their website, and what you are going to see is the thing that is seen on the screen. On the screen you will find that bright spots appear. These bright spots, each one of them is a single electron arriving at the screen. Okay.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
So, therefore, you have seen the video and you can see that this is data from an actual experiment, and the interference patterns are clearly visible, and this indicates that electrons do have a wave associated with them. Also, it has shown you that electrons arrive one by one, and therefore, they resemble bullets, and so they have to be referred to as particles, but these are particles which also have a wave nature. Okay, this is the actual paper in which this data was published. It is of great interest to anybody who is interested in physics, particularly quantum physics. In fact, somebody had put together a list of 10 most interesting experiments ever carried out in physics. A list was prepared, and I think this is actually either number 1 or number 2 in that list. So, this is considered to be among the most interesting experiments carried out by physicists, and that is the exact reference. But then you see, you have to notice something that has happened in the video. See, the electrons were actually sent out from the gun under identical conditions, right. They were all prepared in the same fashion, they were all coming out of the gun, but then when you look at the video screen, what has happened is that they are arriving at different locations. Right. This seems to violate the basic ideas of doing experiments. You see, if you do an experiment, you would expect that the result will always be the same, and this does not seem to be happening in this particular experiment, because if I send out one electron, it may arrive somewhere here at the detector, but the next time the electron is arriving somewhere there, the third time the electron is arriving somewhere else. Right. This is as if suppose you are in the chemistry lab doing a titration. The first time you do the titration, you get an answer maybe 15. Next time you do the experiment, you get an answer of 22.1, and the third time you get an answer of 30.2. And then you would think that, okay, this is not the way science is. The basic idea of science is that experiments repeated again and again should give you the same answer. But here what happens is that when you send out one electron, you cannot say exactly where it is going to be, you can only talk of the probability. See, for example, you had bright regions, and there you can say there is a large probability that the electron will arrive there. You also had darker regions, there you can say, okay, the probability of finding them is small. So here it seems that you can make only probabilistic statements, not exact statements. So then you will ask, in what sense is this particular experiment reproducible? The answer is the following. Suppose you had sent out maybe 100,000 electrons and collected the pattern, then you will get an interference pattern. If somebody else somewhere else in the world does the same experiment with 100,000 electrons and gets the patterns, then your pattern and his pattern will be identical. So therefore the experiment is reproducible only in that sense. But if you are sending out only one electron, you cannot actually say where it is going to arrive, you can only talk of the probability that it will arrive at a particular location, that you can talk about. Okay. And if you wanted to calculate the probability, what is the procedure that you can adopt? The answer is that you have to go back to your wave function. If you actually wanted to find the probability, you will have to calculate find the wave function, and you will obviously be able to say that the probability should be proportional to the square of this wave function. Earlier we were saying intensity is proportional to the square of the wave function. We modify that slightly because we are now thinking of a single electron, and if I am sending out a single electron, I can say, okay, my wave function is going to give me something which is proportional to the probability, that is actually psi square, the wave function square will be proportional to the probability of arriving at any particular location. Now there were great scientists who were very unhappy with this. You see, they thought that if I send out a single electron, it should be possible for me to say exactly where it arrives, but quantum mechanics does not do that. So scientists like Einstein were very unhappy about it. In fact, Einstein made a very famous statement. He said that, you see, the way the behavior of an electron is described in quantum mechanics is not completely satisfactory, because you know that if I had a die and if I toss it, then the answer can be any one of the numbers 1 to 6, and nobody can say a priori what the answer will be. You can only talk of the probability that the answer is a 5 or a 6 or a 4 and so on. And he said, you see, in the case of a single electron, if you are sending out a single electron, you are talking only of the probability that the electron will arrive at different locations, and that cannot be correct. And therefore he made this very famous statement, which is reproduced here: God does not play the game of dice. By which what he meant was that he does not believe in the description of nature using quantum mechanics. He thought that it was not complete. But whatever experimental evidence we have till today indicates that this universe obeys quantum mechanics, and it seems that God does play the game of dice. And again, historically speaking, this kind of behavior was actually first observed in the case of light. So by this what I mean is this experiment regarding wave particle duality or dual nature of microscopic things was first observed in the case of light. So, this is a little bit of history, not too much details. This is actually Newton, and he was among the first to propose a theory of light. What he said was that light is a beam of particles. This was his suggestion, even though before him Huygens had suggested that light exhibits interference, and therefore you have to think of it as waves. But you see, Newton was much more well known than Huygens, and because he was so much more famous, people simply accepted what Newton said and they discarded the wave theory of Huygens. But then later on what happened was Maxwell came along, he formulated what is known as the electromagnetic theory of light, according to which light has a wave nature, and this was accepted. It could explain so many experimental phenomena, and therefore the theory of Maxwell was accepted until Einstein came along, and he said that in order to explain the phenomenon of photoelectric effect, the experimental observations in photoelectric effect, you have to assume that light has a particle nature. So, all the experimental observations regarding photoelectric effect could be explained assuming that light has a particle nature, it is a beam of particles. But even though Einstein made this suggestion, nobody believed him. This suggestion was made in 1905, and there is this person Millikan who won the Nobel Prize. He did not believe in the suggestions of Einstein, and he wanted to disprove them, and therefore he did a series of careful experiments in photoelectric effect, and to his surprise found that whatever Einstein had suggested was completely correct. So, then came along Compton, and he did scattering experiments in which X-rays were scattered from a piece of metal, and there was a change in the wavelength caused by the scattering, and he could explain this by assuming that the scattering process is nothing but the collision, or it is similar to collision between two billiard balls. You can imagine you have the particles of light, which we now refer to as the photon. They collide with the electrons of the metal, something like the collisions between two particles, and all the experiments could be explained using a particle picture. But then of course, it is also known that light exhibits the phenomenon of interference, and therefore it has a wave nature, and therefore scientists were very puzzled. So, they were puzzled because you see, it appeared to them, this is only a joke, it appeared to them that on Mondays, Wednesdays and Fridays light seemed to behave like a particle, while on Tuesdays, Thursdays and Saturdays it seemed to behave like a wave. And naturally, if that is the way it is, you have the question, what about on Sundays? Well, scientists of those days, this as I said is only a joke, scientists of those days would go to their place of worship and perhaps pray to God as to a clarification whether this is a particle or a wave. But now it is clear to us, actually it is quite well established that light has a dual nature. Not only light, it appears as if everything in this universe has a dual nature, right? Even electrons, neutrons, protons, helium atoms, C60, which is a rather big molecule, this also has been demonstrated to have a wave nature. So, people have been trying to show this wave nature experimentally. For different particles, they have succeeded for electrons, neutrons, protons, even for bigger systems like C60. But of course, you see, we do not have experimental evidence for much bigger systems. If somebody says that I have a wave nature, I mean, I being a big particle, you can say, okay, I would probably be expected to have a wave nature. There is absolutely no experimental evidence for that. Though we would like to extrapolate and say that even bigger objects have a wave nature. So, this is a C60 molecule, a nice football shaped object, and I want to show you experimental data taken from the group of Anton Zeilinger, his name you will see in a second. So, you can see the interference pattern that he found. Okay, you can see this pattern, which is just an interference pattern, and this is obtained using a beam of C60 molecules. He made a beam of monoenergetic C60 molecules, passed them through 2 slits, and then observed this experiment, this interference pattern, showing that even a C60 molecule has a wave associated with it. Okay, these are pictures taken from his website. You should have a look at his website, whose address is given here. Okay. Now, though few words about these 2 pictures. Actually, this is again another joke. These 2 pictures. Suppose you are playing football and imagine that the ball has a wave nature, then what will happen? Right, I mean the ball has a wave nature, and let us imagine the wavelength is rather large. Suppose that is not the actual way it is. Then suppose you see I am standing here, I am the goalie, and one of you is going to stand there, and it is a kick penalty. So therefore, you are going to shoot the ball. Now suppose you shoot it directly at me. In our classical world, what will happen is that if you shoot it directly at me, and if I do not move, I mean obviously it will not be a goal, because the ball will hit me and it will go off somewhere else. But if the football had a wave nature, what is going to happen is that the wave associated with the football can go through this side of me or through the other side of me, and right exactly at my back, what will happen? It will be constructive interference exactly at my back. So therefore, even though I am standing obstructing it, it can directly go, and it can be a goal, right. Of course, this will not happen if you do not have a wave nature associated with the ball, which we do not have in our real world. I mean the wavelength associated with the football in our real world we would expect is very small, and therefore you do not see any interference effects. Okay, well, as I said, people have been doing experiments. They have been able to demonstrate wave nature for bigger and bigger systems. What I have here is a report that has come out only 2 or 3 months ago. I suggest that people should have a look at this paper, published in Nature Nanotechnology. The reference is here. The experiment is done with thiocyanins. So you are going to see another video now. Okay, 2 of them. So this is the molecule thiocyanin. You can see it, and these are the single thiocyanin molecules arriving at the detector, at a detector screen. The spots, just like the electron experiment. These bright spots that you see are single thiocyanin molecules arriving after having passed through 2 slits, and you can see the interference pattern that has resulted, demonstrating that these also have a wave nature. Okay. So the interference patterns are very clearly visible. Again, I mean one more video from the same set of people, there is much shorter one which shows the pattern very clearly. Okay. Well, this actually demonstrates that microscopic things have a dual nature. They can behave like a particle, they can also behave like a wave, and we human beings actually have no direct experience with such things. You see, in our world it seems that you see if I have a particle, it behaves like a particle, it does not behave like a wave, and if I had waves like waves on the surface of water, then that is a wave, it is not a particle. For example, there is no bumpiness, there is no lumpiness associated with waves on the surface of water. So we have unfortunately no direct experience of things which have this dual nature, and therefore we find it very difficult to comprehend how can the same object behave like a wave as well as a particle. To help you in that direction, I have taken a picture from the web. This has nothing to do with wave particle duality, it is just a picture that has a dual nature. So, if you look at this picture and if I asked you whom do you see in this picture, what would be the answer? Well, this picture interestingly has a dual nature. If you are very clever, then you can see that there are two people in the picture, but normally what happens is that people can see only one person. So, where are these two people sitting in the same picture? The answer is here. Suppose you say that this is the chin of a person, that part of the face, and that is the mouth, and then that is the eye. Then obviously, I mean, if you imagine that way, then obviously this is the picture of an old woman, old lady. On the other hand, suppose you now say, okay, imagine this as the chin of a person, imagine that as the chin of a person, and then this will be the nose, that will be the ear, and the face of this person is tilted away from you. If you imagine that way, then obviously this is the picture of an young girl, and therefore this is a picture that has a dual nature. As I said, this has absolutely nothing to do with wave particle duality, it is just a picture which has a dual nature. So, if you are asked whom do you see in the picture, then you see, you can say an young girl or perhaps her grandmother. Okay. We will, I mean, the morning the lectures are over.